Welcome to the Deep Dive, your shortcut to being well-informed. Today, we're diving into something pretty exciting, maybe even a bit futuristic. Truly autonomous AI agents. Imagine an AI that doesn't just, chat or find info, but actually does things for you in the real world.
Right. Stuff like managing a really complex calendar, maybe booking travel from scratch, or analyzing data and giving you the insights, all on its own.
That's the dream, yeah. And it feels like it's getting closer. So for this deep dive, we're going to explore the cutting edge of these self-sufficient AIs. We're really looking at how well they actually hold up when you ask them to use different tools in situations that feel, well, real.
And there's a new benchmark for this, right? LIVEMCP-101.
Exactly. We'll be unpacking that. It sounds like it's designed to really push these systems. Our mission today, then, is to give you a clear picture of what these next-gen AIs can do now, but also critically, where they still fall short.
You should walk away understanding why even the smartest models can stumble, the types of mistakes they make.
And, importantly, where research is heading to make them more reliable. Get ready for, hopefully, some surprising facts, maybe a few aha moments about AI getting truly autonomous. Okay, so let's start with the big picture. We're seeing AI move beyond just, text generation. They're learning to interact, use tools. What does tool calling actually mean here?
Yeah, tool calling is, it's basically giving the AI the ability to find, use, and coordinate other software or services.
Like external capability.
Exactly. Think web search, working with files on your computer, doing math calculations, or even talking to APIs, booking things, getting livestock data, that kind of stuff.
Okay.
It massively extends what they can do beyond their training data, gives them real-time access.
And this model context protocol, MCP, how does that fit in?
MCP, it's a really powerful standardized framework that helps make that integration smooth. It's like a common language, so the AI models can use all these different tools without bespoke setups for each one. It's honestly pretty foundational for autonomous AI.
Sounds incredibly powerful, almost like giving the AI hands digital hands.
Sort of, yeah.
But our sources are hinting there's a catch. Systems that look great in the lab. Well, they often don't perform so well out in the wild in real production environments. Why is that gap, that reliability gap, such a big barrier?
That is precisely the issue. The core problem is that, well, the way we've been testing these agents, the benchmarks, they often fall short.
Oh, so...
They might focus on just, say, a single tool call. Or they run in these clean, unchanging synthetic worlds. Maybe they only test a handful of tools.
But the real world isn't like that.
Not at all. Real tools give different answers over time. User requests are full of nuances and constraints. And, a single task might need dozens of tool calls across totally different areas: finance, travel, data analysis.
Right.
Existing tests just don't expose the weaknesses that pop up when these agents hit that complexity. They're just not stressful enough.
And for you listening, if you're hoping for an AI assistant that can actually handle complex stuff reliably,
then understanding these challenges is crucial. It directly impacts how useful these things will actually be for you. It's not just academic theory.
which brings us back to LIVEMCP-101. It sounds like this benchmark was built specifically to address those shortcomings. How did they make it so rigorous, so reflective of the real world?
LIVEMCP-101 is definitely a step up. It's got 101 carefully put together real-world queries. And these aren't simple things. They demand coordinating multiple diverse tools using MCP.
Like what kind of tools?
Oh, everything from web browsing, file operations, math, data analysis, the works. And how they made the queries is interesting, too.
Oh, yeah.
They used LLMs to help generate and refine them, but then had multiple rounds of manual review to make sure they were complex, practical, and importantly, that you could objectively check the outcome.
So verifiable results.
Exactly. And they split them into difficulty levels.
Okay.
30 easy, 30 medium, and 41 hard tasks. It's meant to really find the breaking points.
Okay, can you give us a flavor? What does an easy versus a hard task look like in this benchmark? I'm curious about the complexity jump.
Sure. An easy one might be something like generate a markdown report listing the 5 most recently opened issues in this specific GitHub repo, but ignore the pull requests. Requires tool use, but it's fairly contained.
Okay, makes sense.
A medium task could be, say, searching YouTube for AI-generated art tools. Then, for the first 5 videos, calculate an engagement rate, maybe views divided by duration, and put those results into an Excel file. More steps, data manipulation.
Wow, okay, already getting pretty involved. What about hard?
Yeah, the hard ones really ramp it up, like that NBA example you hinted at earlier.
Yeah.
The agent gets a cryptic clue about an NBA team. First, it has to figure out the team, find its official info, then calculate a game date exactly 60 days from today, then search Airbnb near the arena for places within a specific budget and walking distance.
Whoa!
And then compile all that multi-source information into a detailed markdown report. That requires serious planning, reasoning across steps, handling constraints.
That sounds exactly like something you'd ask a human assistant to do. A whole mini project.
Precisely. It's designed to mimic that level of real-world complexity.
And the way they evaluate it is new, too, right? They're not just checking the final answer.
Exactly. That's key. Because, like we said, real tools change their outputs over time. Search results shift, listings disappear. A fixed, correct answer just doesn't work reliably.
So how do they handle that?
They use this clever parallel approach. Two agents run the task at the same time. One is a reference agent.
Okay.
It strictly follows a pre-validated, step-by-step, ground truth execution plan designed to get the right outcome under current conditions. The other agent is the one being tested in the cloud. It works autonomously, analyzes the query, picks tools from a big pool.
A pool that even includes distractors. Things designed to mislead it.
Yes, exactly, to make it harder. The tested agent schedules calls, processes results, all on its own.
And this parallel setup, you mentioned it tackles temporal drift. Can you unpack that a bit more? Why is drift such a headache for AI evaluation?
Great question. Temporal drift just means things change over time. Search results today aren't the same as tomorrow. Stock prices fluctuate, news updates.
Yeah.
If your benchmark assumes a single static right answer from last week, you might penalize an agent unfairly for getting the correct answer today.
Ah, I see.
Running both agents simultaneously means they face the exact same live conditions. It cancels out the drift effect. So you can fairly compare the tested agent's actions, its planning, tool choices, how it handled the outputs against the reference agent's validated path.
So it lets you pinpoint where things went wrong, not just if the final answer was off.
Precisely. Much more fine-grained diagnosis.
And they measure things beyond just success-fail, right? Like trajectory score.
Yes. Task success rate is one metric, but also average result score, how good was the final output, and average trajectory score, which basically scores the quality of the process. Was the logic sound? Was it efficient? Did it pick the right tools in the right order?
That does sound like a big leap forward in evaluation. But I wonder, does running two agents like that add a lot of overhead? Computationally? Or is there subjectivity in that ground truth plan?
Good points. Yes, it's definitely more computationally expensive than simpler checks. But the argument is the diagnostic depth you get is worth it. As for the ground truth plan, you're right, there's always a potential for some subjectivity. But they mitigate that through careful, expert human validation of those plans. The goal is to make them as objective and optimal as possible. It's a trade-off, but it seems much more robust than alternatives that ignore the process or the time-varying nature of tools.
Okay, makes sense. So they put these cutting-edge models, these frontier LLMs and agents through this really tough course. What were the big takeaways, the headline results?
Well, the most sobering finding, perhaps, is that even the very best frontier LMs scored below 60% on overall task success rate.
Wow, less than 60% across all tasks.
Across all 101 tasks, yes. It really highlights this significant gap between where the tech is and what's needed for truly reliable autonomous performance in complex real-world scenarios. Less than 6 out of 10 times succeeding. That's a reality check.
That is lower than I would have guessed. So maybe something like GPT-5 is leading, but even it struggled, especially on the hard tasks. What was the score there?
Yeah, even the top performer only hit about 39% success on those hard tasks.
Yeah.
Shows how much headroom there still is. And interestingly, while open source models are improving, there's still a noticeable gap compared to the top closed source ones on these kinds of agentic tasks.
And you mentioned the trajectory score, how well they planned and executed the steps. Did that correlate strongly with success?
Absolutely. Very clear correlation.
Right.
Better execution trajectories, meaning, smarter tool selection, getting the parameters right, handling the tool outputs properly, directly led to higher final result scores and higher task success rates.
So it really matters how the AI gets to the answer.
Definitely. It's not just about the destination, the journey counts. A logical, efficient path seems key to consistent performance.
Okay, now this is something I found really fascinating, the findings on token efficiency. Can you explain that? How are these AIs using their sort of thinking budget, their tokens? What's this log-shaped curve they found for closed source models?
Right. This gives us a really interesting window into their reasoning process, if you can call it that. For the top closed source models, like GPT-5 perhaps, they saw performance, the success rate, jump up quickly with just a few tokens.
Okay.
Those initial tokens seem to be used for high-impact stuff, understanding the task, initial planning, maybe probing a key tool, big gains early on. But then the curve flattens out.
Plateaus.
Exactly. Adding more tokens beyond a certain point didn't help much more. It often led to redundancy, like the AI explaining itself more, or repeating checks it already did rather than finding new, useful evidence or making better decisions. It suggests there's a kind of limit to the useful intelligence per token.
Interesting. So just throwing more compute or a bigger context window at it doesn't guarantee better complex reasoning.
It seems not beyond a point. Meanwhile, the open source models studied had a harder time converting tokens into reliable actions at all. They might use a lot of tokens, be quite verbose, but without that corresponding jump in success rates. Less efficient, you could say.
That's a really crucial insight for anyone building or using these things, isn't it? Suggests there are deeper architectural or alignment challenges beyond just scaling up.
Absolutely. It points towards needing smarter, perhaps more focused reasoning, not just more processing.
Okay, so knowing that they fail is one thing, but understanding why is often more useful. The research did a deep dive into failure modes, right? Identified common ways these agents stumble. Can you walk us through a couple of the big ones?
Yes, this is where you get those aha moments. They broke errors down into roughly 3 buckets: issues with planning or coordinating tools, errors in the parameters sent to the tools, and problems handling the outputs from the tools. Now, one of the most common failure types, even for the best models, was semantic errors.
Semantic, meaning related.
Exactly. The parameters the agent sent to a tool were perfectly formed, syntactically correct, like a valid database query structure, or a well-formed search string. But the content was wrong for the task's intent.
Can you give an example?
Sure, maybe it searched for information about the wrong company, or used the wrong product ID when querying a database, even though the query looked fine. It shows a gap in truly grounding the reasoning in the task's context and constraints. It followed the format, but missed the point.
That sounds tricky, like it understands the language structure but not the real-world meaning well enough.
Precisely. Now, another big one, especially for some open source models they tested, like Llama 3.370b Instruct, was syntactic errors.
So the opposite kind of problem.
Right. Here, the parameters were just plain wrong, badly formatted. Maybe the wrong data type, like sending text where a number was needed, or missing fields, or using a structure the tool's MCP server just couldn't understand. The request fails before it even really starts.
Why would that happen more with some models?
The paper speculates it might be because MCP, this protocol, really took off after some of those models were trained. So they might lack specific fine-tuning on how to correctly format those MCP tool calls.
Ah, so that suggests a clear path for improvement at least.
Potentially, yes.
Yeah.
Targeted training on MCP schemas could help a lot there. And then there was one more I found really interesting: overconfident self-solving.
Overconfident.
Yeah, this was common in sort of the mid-tier models. The agent would correctly identify that it needed a piece of information, but instead of calling the right tool to get it,
It just made something up.
it tried to answer from its internal knowledge. Basically, hallucinating an answer or recalling something potentially outdated or incorrect from its training data, instead of using the tool design for that exact purpose.
Why would it do that? Seems counterintuitive.
The thinking is that when the planning gets really complex, or there's just so many tools to choose from, maybe making the tool call feels uncertain or risky to the AI. So falling back on its internal knowledge, even if potentially wrong, feels like a safer bet in that moment of complexity.
Wow. Almost a human-like failure mode, bluffing when unsure.
Kind of, yeah. Not what you want in your reliable assistant, though.
No kidding. So it's not just about knowing stuff, but knowing when to use tools, how to use them correctly, syntactically, and semantically, and not just relying on potentially faulty memory.
That sums it up well.
And they also looked at how just the sheer number of available tools affects performance, right? Did having more options help or hurt?
That was another revealing part. For the weaker and mid-tier models, adding more tools, more MCP servers, more choices actually made their performance worse.
Really? Why?
It increases the complexity, the search space for finding the right tool. More chances to pick the wrong one. More overhead in just deciding what to do. More noise, essentially.
But the top models.
The top-tier models were much more stable. Their performance didn't really degrade much when faced with more tools, including those distractor tools. It suggests they have stronger internal planning and, crucially, better tool screening abilities. They're better at ignoring the irrelevant options.
So robustness in the face of choice is a key differentiator for the best models.
It seems so. Not all AIs handle a big toolkit equally well.
And just to be sure about the evaluation itself, they validated their scoring system. Like, how did they make sure the AI judge wasn't just making things up too?
Good question.
Yeah.
Yes, they did check. They compared the outputs of their automated LLM as a judge system against evaluations done by human experts on a subset of the results.
And
And they found high agreement, which gives confidence that the automated scoring necessary for handling this scale of complex evaluation is actually reliable and reflects human judgment reasonably well.
okay, that's crucial for trusting these results. So let's try and wrap this up. We've gone through Live MCP 101, this really important new benchmark pushing AI agents. The big picture seems to be, well, they're powerful, but still face real hurdles.
Definitely. Significant challenges remain, especially in complex real-world tool use, adapting reasoning on the fly, and even just basic efficiency with their thinking.
Semantic errors, syntactic errors, even overconfidence. Lots of ways to stumble before we get truly robust autonomy.
But the good news is, this kind of detailed analysis also clearly points the way towards how to improve them. It's not just saying they fail, it's saying here's why they fail.
Right. We've seen how this kind of benchmark, with its tricky multi-step tasks and that novel parallel evaluation, gives us much richer insights than before.
That sub 60% success rate, even for the best, is a key takeaway. The token efficiency curve showing diminishing returns.
And that breakdown of specific failure modes, it all paints a much more realistic picture of where AI agents are right now on their journey to interacting effectively with our world.
It's progress, but there's still a ways to go.
So here's a final thought for you to chew on as these agents get more capable and start handling more for us. What becomes more important for your trust? Is it demanding a perfect final answer every single time, no matter what? Or is it maybe valuing a transparent process, seeing the AI's work, its logic, even if it sometimes needs correction, because you can understand how it got there?
And how will this whole push for intelligence per token, for efficiency, shape the AI companions you end up using day to day? Will they be hyper-focused or perhaps more cautious? Something to think about.